We are back on the direct energy conversion systems for sustainability course. This is lecture number 9. In this lecture, we'll talk about thermoelectric power generation. And thermoelectric power generator is nothing but a solid state device that provide direct energy conversion from thermal energy, which is a source being any heat, due to a temperature gradient into electrical energy based on what is called a Seebeck effect. The major drawback of this thermoelectric power generator is the relatively low conversion efficiency, which is typically around 5%. But the power generation offers a promising technology in the direct current conversion of the low-grade thermal energy, such as waste energy coming from power plants, etc. One of the earliest application is the utilization of waste heat from a kerosene lamp to provide the thermoelectric power to power a wireless set. They also been used to provide small amount of electrical power to remote regions, for example, northern Sweden, as an alternative to costly gasoline-powered motor generators. In this particular case, the cost of the thermal energy input must not be considered as a levelized cost of energy calculation, because otherwise they become extremely inefficient to use. And the example of such a device is seen in this slide here. You remember when we talked about the concentrating solar power, you can have a cavity like this in a parabolic trough or a cylindrical trough, for that matter, and where you can have the solar radiation entering into the cavity, and you can capture that heat by putting some window here at the bottom of the cavity so that the radiation will not escape from the cavity. So as a result, the cavity wall gets heated up to, let's say, temperatures of around 1000 Kelvin or anywhere between 600 to 1000 Kelvin. Then this hot surface is connected to a cold surface. Imagine this is a cylindrical vessel, let's say, and so this is the cavity, cylindrical cavity, and outside is an external cylinder here, and this is a cold junction. That means the heat is going to be rejected in this junction, and connected parallelly here are the two dissimilar metals, like the ones we considered in the PV. This can be a P-type material. This can be an N-type material, and they are placed parallelly and connected, and electrically these junctions are connected serially and to a load. And so essentially what you do in the load is where the electricity is obtained and the heat is produced here. So the efficiency of the system is the electrical output divided by the heat input of the system. Generally, when you put several of these junctions together, for example, one P and one N will constitute one junction, and typically that is not that is typically the same as thermocouple, what we usually consider to measure the temperature. And then we put a whole bunch of them together in series, and that is called a thermopile. So this radiation can be obtained in many ways. You can put the waste heat, or you can combust a fuel in the cavity, and you can do many other things with the heat source. And then the typical efficiency, this is a plot which is taken from a master's thesis at MIT, and this is the hot junction temperature, that is the hot surface temperature, which goes all the way in this plot up to 1370 Kelvin. And here is the vertical axis is the efficiency, and the two dissimilar metals are in this particular case silicon or germanium, and this is the lead and telluride and bismuth and telluride. So there are three different material pairs are used in this generator, and the cold junction temperature is about 350 K, and you can see the efficiencies of the system is the maximum you can get about 12%. So these are the low efficient systems, albeit like we said earlier that we use these things when the heat is relatively free. And the single stage thermoelectric device, for example, is shown in this plot here. And here what you see is a silicon and germanium materials which are typically used, and they're sandwiched between ceramic plates. This is the hot plate here, this is the cold plate, and there is a ceramic plate which essentially keeps the heat losses to a minimum, and we connect them. These are the junctions, and we connect them in a series to form what is called a thermoelectric module, and within the module are the thermo elements. We call them as thermocouples. The connection, the junctions connecting the thermo elements between the hot and the cold plates are interconnected using highly conductive metal, which is generally is the copper strips. In fact, that is what you see the plus and minus sign here. And the size of this conventional thermoelectric device vary from 3 millimeters square by 4 millimeters thick to about 75 millimeters square by 5 millimeters thick. They are extremely small. Most of these modules are no larger than about 50 millimeters in length, and the height of the single stage thermoelectric module typically ranges from 1 to 5 millimeters. And the number of thermocouples used to make these modules are anywhere between 100 to 200 thermocouples. There are multi-stage thermoelectric devices that are designed to meet requirements for large temperature differentials. Modules can be up to 20. Such modules can be up to 20 millimeters in height, depending on the number of modules we use. And if you look at a simple module, and this is a single module shown in the picture here, and then we stack them together like the PV, and in this particular case there are 3 modules of different sizes are used. And the power output from most of these commercially available thermoelectric power generators range from milliwatts to about kilowatts. And as we said, in this particular case, the number of thermocouples are around 127, and you can see the area is about 1.35 millimeters of 1.35 millimeters, and the largest one in the table is given as 50 of them thermocouples put in a stack, and the area is about 5 millimeters by 5 millimeters. When you look at the performance of these things, these are experimentally derived performance curves. For about 127 modules of the small thermocouples, you can see with a temperature difference delta T of about 100 Kelvin, you get a power output of about 2 watts. And this is for the very small module. Like we said before, these are few millimeters square area. And the standard thermocouple device typically consists of about 100 or so in size, and they approximately deliver about 19 to 20 watts. The maximum output power from this power generator typically varies, depends on the temperature difference, as you can see here, between the hot and the cold plates and module specifications. In fact, these are different module specifications will give you a different kind of output. And the maximum power output is a function of the temperature difference and also depends upon the different geometries. The maximum power, of course, this increases almost parabolically with increase in temperature difference. For a given temperature difference, there is a significant variation in maximum power which you can see here for different modules, and mainly due to the variation in thermoelectric materials and the geometry of the module and the contact properties. Then you can model this as simply as is shown in this figure here. The system, the basic theory of the thermoelectric device is simply a phenomena called the Seebeck effect, and it was discovered almost in 1921. This simply is when a temperature difference is established between the hot source, in here heat source, and the cold one, which is called the heat sink, and you with the two dissimilar materials connected thermally parallelly and electrically serial connection, and this temperature difference will give rise to a voltage, and current passes through, as we discussed before in the PV. When you have a hot metal, apply the current to it, and you get when you heat it up, electrons will flow through and provide a power, and that is given by the W dot E. Essentially, you can think of this in a first law. There is a heat energy in the hot side flowing into the cold side, and the difference between this energy is equal to the work produced by the electrical power. More than one pair of semiconductors are normally assembled together to form the typical thermodynamic module, and within the module a pair of thermo elements is called typically a thermocouple. The junctions, which are, for example, here this can be a hot junction, this is a cold junction in a thermocouple, generally connected using a highly conducting material. And so what we do is that we take this simple module, and then we will start analyzing this in a simple mathematical form. And essentially what we want to do, we introduce a simple model that explains the underlie the operation of the device. Before we go to that, we are very familiar with what's called Joule and Fourier effects, and Fourier effect is nothing you studied in theory of heat conduction, and Joule is what you have known already in the physics. Is essentially you take a conductor, suppose it is maintained at two different temperatures. One end is called T sub H, which is a hot end, and one is maintained at the cold end, and this the temperature differential bar is now submitted to current here. Like for example, you connect it to a battery, then the heat power is generated on either side end of the bar and is given by this, and the power generated on the hot side is given by Fourier component, which is this is the heat conduction coefficient multiplied by delta T, and this is the Joule energy, and this is given by Ri square, and half of it goes on the hot side and half of it goes on the cold side. So this is essentially power going in the hot side is given by this expression, and power going out on the cold side is given by this expression. In this particular case, R is the resistance of the metal. Now, having this background, now we will get into the analysis of the Seebeck effect, and now it can be applied to a thermoelectric generator in the part 2 of the lecture.